Let's start with Libero SoC, give you a quick overview of the Libero SoC design tool suite. Libero SoC is a comprehensive design tool suite that allows you to implement designs focusing on SmartFusion 2, Igloo 2, RTG4, or PolarFire. You have multiple different methods that you can use to enter your design. You can use a graphical design tool from Microsemi called SmartDesign. You can use your traditional HDL, either VHDL, Verilog, or System Verilog. And we also have embedded design flows for designs that feature processors, either hard processors like we have in SmartFusion 2, or a soft processor like RISC-V or Cortex-M1. Libero includes the Model Sim simulator from Mentor Graphics for functional simulation, gate level simulation, and timing verification after running layout. We have the Synopsys Simplify Pro synthesis tool that allow you to synthesize and optimize your design, entering timing constraints to optimize the performance of the netlist that goes into the layout tools. And then after synthesis, we have layout tools that allow you to do a power-driven or timing-driven layout using timing constraints. We have incremental layout for ECO type of applications where you're going to make a small change. And we have advanced layout options like multi-pass layout to help you meet your timing objectives. After you've completed layout, we have power analysis tools and timing analysis tools that allow you to make sure that you're meeting your timing objectives, and also to understand the power consumption of the design and where the power is being consumed in the design. After you've gone through your power and timing analysis, we have programming tools that allow you to program your design, including the industry's first secured production programming solution that allows you to securely program devices in untrusted environments. And after you've programmed your design, we have the best-in-class debug solution featuring a tool that's called SmartDebug from Microsemi, and we also have another tool from Synopsys that's called Identify that you can use to debug your designs. Libero SoC is easy to learn. We have an intuitive design flow. We have GUI wizards that will guide you through the design process, and it's easy to adopt. We have a single-click flow from synthesis through programming. We integrate industry-standard third-party tools. We have a rich IP library of cores that's available with Libero SoC, and the look and feel of the tools is very similar to some other tools that you may have used from other vendors. Libero SoC has some differentiating features. We have an enhanced constraints flow, where we have a constraint manager that's a centralized GUI that allows you to edit, apply, and manage constraints for your design. These can be timing constraints, I/O constraints, and so on. We already have the aforementioned SmartDebug tool that allows you to take advantage of features built into the Igloo 2, SmartFusion 2, and PolarFire silicon to debug your design without the need for adding additional logic to have an integrated logic analyzer function. And then the secure production programming solution that I mentioned that allows you to program SmartFusion 2 and Igloo 2 devices securely in an untrusted environment. So this is a look at the enhanced constraint flow manager that's available in Libero SoC starting in version 11.7. We had a webinar on this a while ago now. We have one centralized GUI that comes up that allows you to put in your I/O attributes, your timing constraints, floor planning constraints, and netlist attributes. And you have multiple ways that you can enter these constraints, from using an editor and typing in your constraints to using graphical tools. And once you've created these constraints, you can specify the tool that you want to have this constraint apply to. In the case of timing constraints, it could be synthesis, could be place and route, it could be timing verification. You can have a single file that's used for all three purposes, or you could have individual files for each purpose if you wanted to. And here we're showing timing, also some floor planning constraint files with a PDC extension, and then I/O attributes that might be pin pin assignments as well as drive strength and things like that. We support cross-probing between some of the different tools. So SmartTime is our static timing analysis tool, and you would use that to verify your timing after layout. You can cross-probe that with our floor planner tool, which is called Chip Planner, and that can be really useful if you're not meeting your timing because you can see exactly where the cells are placed on the die. We also have cross-probing between the SmartTime timing analysis tool and the SmartTime editor, where you enter your constraints. And this allows you to enter any exceptions that you might have forgot to add before you ran layout if you're doing your verification. So if you go through and you realize a path that has a violation was maybe a false path or maybe a multi-cycle path, you can enter exceptions and then just regenerate the timing without the need to have to go back and run layout again, and then see where you stand with your timing objectives. SmartDebug is the industry's best debug tool. Was first integrated in Libero in 2013, and it allows you to debug your FPGA fabric and your SerDes blocks in the devices that have the SerDes without adding additional logic. So you can bring 2 internal nodes out to dedicated pins real time without having to reprogram the device or rerun layout if you want to look at different pins. We can debug memories. We can debug our transceivers. And all this debugging is done using the FlashPro programming cable that you would use to program. So you don't need any additional hardware to use the debug features. It doesn't use any additional FPGA resources, and there's no need to recompile or reprogram, apart from one feature that's called probe insertion that lets you route signals out to unused pins. Microsemi's secure production programming solution is a way to allow you to take blank devices, ship them to an untrusted environment, and securely program in the keys and all of the bitstream material without exposing those keys. And we do that by using hardware security modules. So we have a hardware security module. This is a hardened processor created by Thales. We have one at the user end. We have one at the contract manufacturer end. And the user would go through and use our Libero software and create a job ticket that indicates the bit stream, the keys are injected, and the number of devices that are authorized to be programmed. And that gets transmitted over to the manufacturing location and used with the HSM at the manufacturing location to allow a certain number of devices to be programmed. So this ensures that the keys are never exposed. The job ticket specifies who can program the devices, which devices are authorized, the exact number of devices that can be programmed. And then a programming content assurance report is set back, so you know after the devices have been programmed that the correct number of devices was programmed, which bit stream was used, and so on. So you prevent overbuilding, you can prevent the wrong bit stream from being used. It's a really secure and easy to use solution to allow you to just drop ship blank devices without the need to program a key in a secure environment and then give the device to a contract manufacturer. So it's available for SmartFusion 2 and Igloo 2 devices today. So I'm going to move on to our Mi-5 ecosystem. So an ecosystem is everything you need for something to thrive. And our Mi-5 ecosystem from Microsemi consists of design tools. I already talked about one of them, Libero SoC. Soft CPUs. We have boards. We have operating systems. And we have solutions. So I'm going to talk about all of these as we go along today. Our ecosystem will continue to evolve and get bigger over time. And we're marketing our RISC-V ecosystem as Mi-5. So RISC-V is a new instruction set architecture that's a standard open architecture under the governance of the RISC-V Foundation. RISC-V is designed to be scalable for a wide variety of applications, easy to implement with regard to size and power, and it's offered under the Berkeley Software Distribution open source license. So Microsemi has 3 different RISC-V soft cores that you can use that implement the RISC-V instruction set. I'll show you them on a slide coming up in a minute here. These cores are freely available through the Libero IP catalog. So when you download the Libero software, you get this IP catalog, and these cores and other IP cores are included in that catalog. Today we have something that's called the RV32MA instruction set that we support. So I stands for base integer, M stands for integer multiplication and division, and A stands for atomic instructions. Our RISC-V offerings have an integrated 8 KB instruction cache and an 8 KB data cache. And you'll see that we have offerings with 2 external AXI4 interfaces, and we have some offerings with 2 external AHB interfaces. We have support for up to 31 programmable interrupts, and the debugging is done through the JTAG interface on the device, and we do debugging with a tool that's called SoftConsole. So this slide shows the soft RISC-V cores that are available today, plus our roadmaps. So at the very top row here, the first one, our core RISC-V AXI4, was the original RISC-V core that was available from Microsemi. It's still available today, has the 8 KB instruction and data cache, and it had an AXI4 interface for the MEM interface and the I/O interface. We had some customers that requested that we replace the AXI4 interface with an AHB interface. And so we brought out a couple of new cores, and we started marketing these as My5. So My5 RV32I MA L1 AHB, which has an AHB interface. It's roughly the same size as the original AXI4 interface, still has the same 8 KB instruction and data cache. That's available today. And then we brought out the RV32I MAF with the AHB interface, which is a single precision floating point unit has been added. So this core has a size of about 26,000 logic elements. And again, it has the 8 KB instruction and data cache. So all 3 of these are available today from the IP catalog. We have plans to bring out a couple of other cores. They should be out in the second quarter of 2018. We're looking at a small core that doesn't have the multiply instructions or the floating point. It's intended to be a smaller core to be used where people might maybe just want something like a software programmable state machine, or to be able to handle small control loops. So that's going to be around 4K logic elements. And you see there'll be no multiply divide and no cache. And then for bringing out a RV32I MA with the AXI interface that will be out in the second quarter as well. So this is about 10K logic elements, but it's going to be basically this the same RV32I MA with an AXI interface instead. And based on customer demand, we're always looking at our mix, so we can add additional cores if we have a particular customer demand. When you get over here to the right, you see the numbering scheme for the cores. So the RV32I indicates the 32-bit integer machine. M indicates multiply and divide. A is atomic instructions. F is single precision floating point. And then L1 is the instruction and data cache. And then the last 3 letters indicate the bus interface, either AHB or AXI. So it might be a little bit confusing because we have these My5 soft cores now, the ones right here, My5 RV32I MA, and we also have the core RISC-V, which was the original core. The My5 soft cores are based on the RISC-V draft privilege ISA spec version 1.10. And the ones that are available today have the AHB interface to access the memory and the peripherals. We support the A and the F instruction set architecture in addition to the RV32IM. I'm going to show you the firmware catalog where we provide drivers and the hardware abstraction layer. These are supported with version 2.1 of the hardware abstraction layer. The original core RISC-V AXI4 was based on the RISC-V draft privilege ISA-spec version 1.9, and it had the AXI4 interface, and most of the peripherals that we provide have either an AHB or an APB3 interface. So using that core required in a lot of cases the use of this AXI to AHB bridge that we provide. So there's a couple of references here, the My5 core details, and also a tutorial on how to build a RISC-V processor system. This shows you a little bit more details of our My5 RISC-V offerings. The My5 RISC-V cores have a 5-stage instruction, or have a 5-stage pipeline. I mentioned the 8 KB instruction and data cache with the integer multiply and divide. They have 2 hardware breakpoints, have 31 31 interrupts that are set, the priority set by the interrupt number, and roughly 10,000 logic elements without the floating point unit, and run in the range between 50 megahertz and 150 megahertz, depending on the peripherals and other things that are in your system. This slide also shows the core mark integer benchmark, which measures the performance of the core. So the larger number is better, and you see the RISC-V number is 2.01. We also show the NEOS and the Microblaze. So you see that we're really competitive with those processors from other vendors, and you see that it's a lot better than the Cortex M1 soft core. So we talked about the ecosystem, and I said that the ecosystem includes design tools. I told you a little bit about Libero SoC already, and all of the different tools that are in there. So you're going to use Libero SoC to implement your design, and then we would use one of our programmers, and here we're showing a Flash Pro 5, to program the board. Here we're showing the future My5 board. After you've programmed the board, then you want to develop your applications, and you can use a tool from Microsemi that's called SoftConsole. SoftConsole is a free firmware development tool that uses the Eclipse IDE and the OCD debugger, and it allows you to create a project, use another tool called the Firmware Catalog that you can download for free from Microsemi, to generate drivers for your peripherals, generate your RISC-V HAL. You can even generate sample projects. Then you can compile, you can build your application, and then we can debug through the JTAG interface using that same programmer that we use to program the board, and you can develop your application. So I'm going to show you a little demo of that as we go along in just a little bit. Now this slide shows a picture of the IP catalog, and this is how we provide these soft cores to you when you're using Libero SoC. So if you look under the processors category, you'll see that here's the core RISC-V I mentioned, and then the 2 My5 processors that I mentioned. And we also have a number of peripherals. So we really have pretty much everything that you would need to build a basic system. And you could always create your own peripherals if you wanted to and bring them into your project as well. In addition to the processors and the peripherals, we have a number of bus interfaces. So bridges like the AXI to AHB that I mentioned. We have AHB to APB3. So we have pretty much all the building blocks that you need to build up a system within the Libero IP catalog. And in the IP catalog, we also have access to documentation. So if you select one of these cores, you have access to the release notes and the handbook. So you can get all of the details of that particular core, including estimates on utilization and different technologies, just by looking at the handbook. Now, when it comes to firmware development, we have what we call the Mi5 software stack here. Down at the very bottom of the stack is the hardware platform, and that's going to be the silicon from Microsemi. So it could be an Igloo 2 device, it could be RTG4, one of our new programmable space devices, or it could be PolarFire, our most recent FPGA offering. Above that, we have the hardware abstraction layer for RISC-V, which allows you to develop bare metal applications. And then we have drivers for all of the individual peripherals. So Microsemi provides all of the things up to the driver level. We provide the hardware platform, obviously, sell the silicon, and in the firmware catalog, you can generate the RISC-V hardware abstraction layer, and you can also generate drivers for all of the peripherals, and then you can also create sample projects. Above that, there are a number of real-time operating systems that are available for RISC-V, and there's various different middleware pieces that can be purchased from third-party vendors. And then above that is the application layer, which differentiates individual products. That's where you would develop your own application. So here is a look at the Microsemi firmware catalog. The firmware catalog is available for download from our website for free. There's no license involved. And this is where you can go to create drivers for the different peripherals and create your RISC-V HAL that you would use to bring into your project. And I'll show you exactly how we'll do that in a little bit. We release new cores. We push them out to you via the web. You can add them to your catalog. They're version controlled, so you see the version number here. Tells you the size. We also have full documentation for the drivers and the RISC-V HAL that are in the firmware catalog. So if you select a particular driver, you have access to the release notes and also the user guide that will describe all of the different functions that are available for you in that driver. Here's a screenshot showing how to create a sample project. So when you right-click on a driver, or if you right-click on, in this case, the RISC-V HAL, we can generate complete little projects that you could bring into SoftConsole and use that as a starting point to use the drivers, become familiar with how to use the drivers, and maybe make some simple application code to run on a target board. And then for RISC-V firmware development, we have the SoftConsole tool set that I mentioned. So SoftConsole is the free firmware development package that you can get from Microsemi. We have a couple of different versions that support RISC-V. I'll show you those in a second. SoftConsole is free. It uses the Eclipse Space IDE, and it uses a GDB open OCD debugging. It also supports a couple of different programming cables. It works with the Flash Pro 5 that I showed you. It also works with an Olmex ARM USB Tiny H. So if you have one of those, you can use that and debug through the JTAG port and develop your firmware applications. When I talked about the ecosystem, I said that another thing in the ecosystem is boards. And we do have a number of different boards that are available that you can use for RISC-V development. We're showing some of them here. We have the PolarFire evaluation kit. There's a new board that just came out that we didn't get a picture of in here. It's called the PolarFire Splash Kit. It's a little bit less expensive than the PolarFire evaluation kit. Both of those devices feature the PolarFire, or both of those boards feature the PolarFire silicon. We have our RTG4 development kit, which has one of the reprogrammable space products on it. And then we have the Mi-5 Igloo 2 Creative Development Kit, which is developed by Future Electronics. This board ships pre-programmed with a RISC-V application in it. And then there's a Sci-Fi Freedom platform as well that you can use. It's been validated with SoftConsole. So there's a number of different boards that are available for you to use to do RISC-V development. And then we have a number of different operating systems as well. There's some open source operating systems like FreeRTOS, Huawei Lite OS, and Minute. There are also a couple of commercial operating systems. There is ExpressLogic has something called ThreadX, and then there's the Microsemi OS 3. Microsemi has been purchased by Scilabs, but Scilabs evidently is still keeping them as kind of almost a separate entity, developing the operating systems like they had done before. So the open source operating systems are available today, as is the Microsemi OS 3 from Scilabs Microsemi. ThreadX is not released yet, but it will be available soon. And where can you get this stuff? Microsemi has a site on Github where you can go and get various different design examples that are targeted to different boards. So these would be complete Libero projects as well as firmware projects. There's a getting started to build a RISC-V tutorial. There's also the hardware abstraction layer port from Cortex-M. So you could move from a Cortex-M series to a RISC-V if you wanted to do that. So this is a look at the GitHub site. If you want to access the GitHub site, if you just Google Microsemi RISC-V GitHub, it'll bring the link up for you. You can go out there and you can see all the information that's out there. We have examples that target various different boards. And here's some links for some available collateral as well. Our Mi-5 embedded page, information about that Mi-5 creative board, the yellow board I showed a few slides ago, and then the tutorial on how to build a RISC-V design tutorial. We also have another one that we're working on for PolarFire, the PolarFire Atheno crypto core with RISC-V. You can see some of these here. Okay, so that was kind of quickly going through the ecosystem and some of the different pieces to make you available or make you aware of what's available. Now I'd like to kind of move into SoftConsole a little bit more, and I'm going to have a lot of slides, but I'm going to skip the slides and just go right to the tools. I think that'll probably be more instructional as we go through this. As I mentioned, SoftConsole is free. It supports the RISC-V cores as well as ARM cores. Those ARM cores could be a soft Cortex-M1, or it could be the hard Cortex-M3 that we have in our SmartFusion silicon and our SmartFusion 2 silicon. Mentioned that SoftConsole is based on the Eclipse IDE, and we use a GDB open OCD debugger. SoftConsole is available for either Linux or Windows hosts. And it supports different dongles, as we mentioned earlier. It's customized for Microsemi processors, so we have a group in Ireland that pulls all these pieces together. And it comes bundled with example projects, and you can take advantage of those example projects to kind of accelerate your development as you go through. And I'm going to show you how you can do that in just a minute. Now, if you look at our website, you'll actually see there's 4 different versions of SoftConsole that's available for download. If you're going to do anything with RISC-V, it gets narrowed down to only 2 versions that are available for you to use. There's a version 5.1. It supports Windows and Linux, but it only supports the original RISC-V core that we mentioned, the core RISC-V with the AXI4 interface. The latest offering is 5.2. It's also available for Windows and Linux, and it supports all of the RISC-V cores. So my recommendation would be, if you're starting out, just download 5.2 and just ignore any of those other versions that are still up there on the website. At this point, what I'm going to do is I'm just going to stop the presentation and I'm going to jump over to the tools, and I'll bring up SoftConsole and I'll show you how I could take advantage of one of those example projects that gets installed under the Libero installation. And I'll walk you through all of the steps that you might take. Say if you had the Future Creative board, you pull it out of the box, it's pre-programmed with a RISC-V core in it and some peripherals. Well, how would you develop the code? So let's just jump over to the software and take a look at that. Let me move some things around here. Before I do that, I just wanted to bring up Libero here quickly. This is my Libero project, and this is my My5 design that was implemented using our graphical tool called SmartDesign. This is the My5 core right here. This little JTAG interface that allows me to go through the standard JTAG ports, and I can do my debugging. That's what we're going to do with SoftConsole. We use some internal oscillators in a PLL to generate our clocking, so that's what you're seeing over here. And then I have the MEM bus, the cached bus, that's going through this AHB Lite interface over to an internal memory block. So in my application, the design is running from an internal LSRAM block. There's other applications that you could come up with, and you could use DDR memory on a board, for example. But I just put this together quickly for these demo purposes, so I just use this internal RAM. I'm just going to run a small application. Then we have the uncached bus here, the MMIO bus. That also goes through this AHB Lite bus interface, and it goes down to 3 peripherals that I'm using. I have a UART, I have a GPIO peripheral, and I have a timer. So all of these are available in the catalog. Let me just show you the catalog here. This is the catalog. There's the processors. Here's the peripherals. So came out of this group here. And then these bus interfaces, the AHB Lite bus interface and the AHB to APB3, those are all out of the bus interfaces catalog. So all of these building blocks are provided in the Libero IP catalog. Then I put this together, and I went through and I put in my timing constraints and went through my design flow and programmed my board. So once I've done that, and I want to start developing my application, then I'm going to use SoftConsole 5.2. So I've got SoftConsole 5.2 up. Now I could start from scratch, and I could create my project, and I could look at the release notes. So release notes will tell you everything you need to know as far as your project settings, and I'm going to walk you through those. But a shortcut way to do this would be to take advantage of some of the example projects that we provide. They're provided under the install, where you install Libero SoC 5.2. So I've got I've got SoftConsole open, so I'm going to import an existing project. I'm saying importing existing projects into my workspace. The workspace is just where I'm setting my project up. I'm going to browse out, and I'm going to look under where I've installed SoftConsole 5.2. So here's my SoftConsole 5.2 installation, and in the extras workspace examples folder, you see there's a number of examples out there. So I'll just check that. Now some of these aren't even RISC-V projects. There's a Cortex M1, for example, and so on. So I'm just going to uncheck most of these, and I'm just going to keep this SysTick Blinky project. And I'm going to bring that right into my workspace. So I'm going to say Finish, and here's my project. And my project includes drivers for peripherals, the GPIO, and the UART. It includes my RISC-V HAL. And included in that RISC-V HAL is a linker script. We'll talk about that in a minute. The linker script is used by the linker to specify the execution areas. I have a hardware platform file, and I have a little application program here. And in this application program, it's just real simple. We define a little message here, a hello message. We configure the UART, we configure general purpose IOs, and we configure the SysTick timer. And when we get an interrupt from the timer, we just put a different value up to the general purpose IOs, and I have the general purpose IOs connected to LEDs on my board, so that'll make my LEDs blink, and I can open a terminal emulator and I can see this message appear. So it's not a real exciting project, but it has all of the pieces that you might use, and it shows you how you can take advantage and use those drivers and so on. Before I go ahead and try to run this application, there's a few things that I should do. In order to make sure I have the latest version of the drivers, I'm going to bring up the firmware catalog here. I mentioned the firmware catalog, so here it is. And we may have introduced new drivers since I installed SoftConsole, which means that the drivers that are in my example project might not be the latest. It might be okay, but what I could do just to be sure that everything is the most current is I could go out and I could generate new drivers. So you see I can just right-click and I can say generate, and I could generate new drivers. Yes, I can find out details about this core. I could access the documentation, and I can even generate some sample projects using this particular core if I want to. I'm just going to generate these drivers, and I'm going to point to my project here, and it's going to tell me it's going to overwrite the drivers that are already there, and I'm going to say yes. So I'm just doing this to make sure that I have all of the latest drivers in my example project.
Hello, Tim?
Yeah.
Okay.
Okay, so that's finished. Tells me I wrote those files out. Close that. I'll tell you what I'm going to do. I'm going to try to be bold here. I'm going to not do the drivers from the UART just because it took a little bit of time, but I'm going to do the RISC-V HAL. I had a slide that said RISC-V HAL had to be 2.1 or later. So you see I have a couple of them here. I've got to make sure I choose the right one. I'm going to generate this, put it in the same place. It's going to ask me if I want to replace existing files. I'm going to say yes. I'm going to wait for a minute or so. And then I'll have the latest version of the RISC-V HAL and the latest version of my core GPIO, and I think the UART will be okay. We'll see. So sort of reiterate what we've done so far while we're waiting for this. So we opened SoftConsole, we picked a workspace, we imported the example project, and then I went through and I used the firmware catalog just to update the drivers and update the RISC-V HAL. You see it told me it wrote this out, it shows me all the files that were written out. Okay, so that's the first step. The next step, I have a hardware platform file here, this hardware platform.h, but the hardware platform file doesn't necessarily match my design. And so I'm going to open this, and I'm going to bring up the memory map. Where'd that go? Hang on a second here. Here we go. My Libero project I showed you, I generated the data sheet for that, which includes the memory map. So I'm going to show you the memory map here for my system. I'm going to kind of look at that while we look at what's in the platform header file. Here we go. So There's a big section here in the platform header file for a number of different peripherals, but you see the peripherals I have are at a different address. And also there's the system clock frequency in here. This is set up the default values that are in the hardware platform file are for a 50 megahertz system clock, but when I implemented my design, I used a 120 megahertz clock, so I have to change that. So it's 120 megahertz. This is used to figure out like the baud rate calculations and things for the UART. So if I get that wrong, I'll see a bunch of garbage characters in my terminal emulator. Then the next thing I need to do is I need to update my addresses here. So the address for my UART is 6,000. Oops, one too many there, it looks like. Core GPIO is 6,000, 1,000. Now these choices were made when I made my system, so you could design the system and have different addresses if you wanted to. This is just the addresses that I used in mine. 6,000, 2,000 for my timer. I could just ignore those other ones, but there's another one here, GPIO out, that gets used for writing out the GPIO. That's the same as a GPIO, so I'll just fix that one too. 6,000, 1,000. Okay, it looks good, so I'm going to save that. So we've gone through, we've changed the memory map in the platform header file. The other thing that I should look at is I should look at my linker script here. The linker script is used by the linker to specify the execution areas and so on. And you see there's a memory length in here of 64K. I didn't implement my design with a memory that was that big because I was just going to do something very simple. Mine's only about 24K bytes. So I'm going to change the size here just so that I can catch it if the code should get too big. Then the linker will know that I only have 24K to work with. So I'm going to save that. So again, we brought in the project, we updated the drivers, the RISC-V HAL, updated the hardware platform file, make sure that the system clock rate matches our design and the memory map matches the design. Then I updated the linker script to make sure that the memory size matches what's in the linker script. Next, I would have to go in and set some project build settings. And in these example projects, the settings are already made, but I'm just going to open these up and I'm going to show you what they are. If you create a project from scratch, you can always open an existing project like this and then open another copy of SoftConsole because you're going to have more than one copy open at a time. Create your project from scratch and you can just compare these project settings. So I'll go to the project menu, choose properties, and then I'm going to choose under C++ build, I'm going to choose settings. And I want to look at the target processor, and I want to make sure, in this case, that the architecture is the RV32i. If we had a 64, if we brought out a 64 core, you see there's some different choices here. We have the multiply extension. The core I'm using also has the atomic extension, so I'm going to check that. I didn't use the floating point version of the core, but if I did, we have the choices there for single precision and double precision and so on. So I want to go through and I want to set those. And then a couple of other things. I may need to put in the paths for the compiler in order to find the files. If you try to build your project and if it says it can't find any of the files, and they're right here, I can see them in the Project Explorer, it's because you didn't set the includes. So you can hit the little add button, you can navigate through your projects to the different folders, and you see that that's what was done here. We're pointing out the drivers, GPIO folder, UART, APB, and so on. Another thing is we have to set the path to the linker script. So we go down under linker and we choose general. And you see we already have this pre-populated. We're looking at this the Microsemi RISC-V RAM.ld file, which was our linker script right here. But if you created a project from scratch, none of this would be set. So you'd have to do that yourself. And you would do that by, you can click this button, the Add button, and navigate through your project and point to the linker script that you want to use. Another really important one is this do not use standard start files. This needs to be checked for the RISC-V processors. And then finally, there's a couple of optional things that you could use if you wanted to. One is that you can go under the miscellaneous settings for the linker, and you can choose to use what we call newlib nano. So SoftConsole comes bundled with a standard library, and newlib nano is a small version of that library. It's even smaller when it builds your executable. It can make a smaller executable, but will eliminate certain functions like full printf formatting options and things. But it might be that you don't really need all of that capability. So if you're not using that, and if your code size is getting a little bit big, you can check the Use newlib nano option here before you build your project. Okay. So once I've done that, I can just say Apply and Close. And now I'm ready to build my project. So again, we brought the project in, updated our drivers and our RISC-V HAL, made sure our hardware platform file matched our design, made sure the linker script matched the size of the memory we were executing from. Then we checked our project settings, and now I can just choose Build All from the project menu, or I can just click the little icon right here. I can build my project. And in the console view, I'll see messages that come up from all the different tools that were run. And if I look at the problems view, hopefully I'll see no errors. If you had any errors or any warnings, they would show up in this view, and then you can look at the console view to get more information. Okay, now that I've done this, I'm just about ready to launch the debugger. But what I need to do is I need to create a debug launch configuration. There's also a debug launch configuration that's created in the example project. So you can go to the Run menu and choose Debug Configurations, and you'll see there's one that's already there. In fact, I'm going to delete this guy. I created one earlier. This one comes with the project. It's this RV32M Blinky debug. And let me just close this for a second. When I built the project, I used a build configuration that was called debug. Let's just go back to the project properties real quickly. See, it says configuration debug active. When I built that project, it created this folder called debug, and it creates this little executable down here. This file here, this with the .elf extension, and that's what we're going to use in our debug configurations. So I have this debug configuration that's already there. I have the name, the project, and then you see the debug folder in this little elf. If you create something from scratch, you could right-click or double-click and say New, and it'll put a name in here. It will put in your project, and it should put in a little debug elf. So you'll see that, and then you want to go to your debugger tab, and you want to check a couple of fields here. You want to make sure that the config options includes this line --file space board / Microsemi -RISC-V.cfg. This is a configuration file for the RISC-V boards. It's included in the files when you install SoftConsole 5.2. And then down here in these commands, you want set mem inaccessible by default off, and set architecture RISC-V RV32. Okay. Once you've done this, you can hit the debug button and you're ready to launch the debugger. And again, if you're creating a project from scratch, you could just look at another example project and see those settings and just match them. When I launch the debugger, it's going to ask me if I want to open a new perspective. So a perspective is a collection of windows, which we call views, and there's two of them that we use by default. There's the C, C++. This is where I developed my code, where I did my builds and everything. And then there's the debug perspective, where I'm actually running the debugger. And the debug perspective has views where you can see variables, you can see breakpoints. By default, there's a breakpoint that gets set at the first executable line in main. So you see the code downloads and then it stops. I can see registers, see the registers for the RISC-V processor. I can open a view. I have it open here. It's the disassembly view, so you can see the assembly code. And at this point, I could start, I could single step if I wanted to, or I could hit the execute button. Now, I told you that there was a UART in this design, and we were going to send a message. So we've got a terminal emulator that's built into Libero SoC, or I'm sorry, into SoftConsole. And I'm just going to create a new one here. So I'm going to create a serial terminal, and on the particular board I'm using, which is the PolarFire Splash Kit, there's actually 4 different COM ports that come up, and the third one is the serial terminal. So I'm going to choose that. The baud rate and the data size are tied to what was implemented in the code, and we set this up for a baud rate of 115/200. So I'll say OK. Then I'm going to start the code, and I'll see my little welcome messages here. So remember that was up here in main, our welcome message. So there it is right there. And this also drives LEDs on the board. And I have a webcam here, so I'm going to bring this up to see if you can see my LED. So this is my board, my PolarFire Splash Kit, and you can see these LEDs are moving. These are going to change every time I get a timer interrupt. Okay. My design drives out 4 different GPIO outputs, but you see this LED is not changing at all. And the reason for that is if you look in the code, in our interrupt service routine, we come in here and we're going to shift, and it says if the state is greater than 4. So it's really only going to drive 3 LEDs. So if I just want to demonstrate making a change quickly, if I change that to 8 and I save it, then I come back and I do a build. Check the problems view when I'm done, make sure I didn't screw anything up. Hopefully I didn't. Okay, no errors, that's good. Then I'm going to right click on the ELF here, and I'm going to say terminate and relaunch. This is going to download the new code that we just created. And now that that's there, I'm going to hit the run button. Let's go back to my webcam. Now you can see this LED is blinking now, right? So now I'm driving 4 GPIO outputs instead of just 3. And I could have gone in and changed the message if I wanted to. You can single step. You can click in the margin here and set breakpoints, and then you can single step in the C code or in the disassembly view if you want to. You can create memory monitors. So you can do all of the standard debug type of things that you would do. So let me just kind of wrap up here, and then we'll see if there's any questions. So the benefits for our Mi-V ecosystem, from the standpoint of using RISC-V, it's royalty-free. So that means a lower cost for the end users. You can move to an ASIC or another device without paying any NRE. The instruction set architecture is frozen, so that preserves your software investment. You don't have to deal with new versions coming out. Your code won't work. And it's available for the availability of open source RTL for inspection enables trust. And then the Microsemi Mi-V ecosystem provides firmware and hardware engineers with a comprehensive ecosystem from a tier 1 vendor. It allows third parties to access the growing platform to further RISC-V adoption and innovation. PolarFire FPGAs are cost optimized. They can boot from on-chip flash to prevent malware and rootkit type viruses. I didn't actually go through that in any kind of detail. I'm running this application on a PolarFire device. It's running because I'm downloading to the RAM. But I could take that hex file that was created and I could store it in an internal non-volatile memory in the PolarFire device and have the RAM loaded at power up so that the application would run and I wouldn't need my debugger. We have our RTG4 radiation tolerant FPGAs, and then we have our Igloo 2 FPGAs, which have big blocks of on-chip flash. Again, you can boot from those devices to prevent malware and rootkits. So we have lowest power FPGAs. We have RTL available for customization for your applications. We have design IP, security, and SEU configuration immunity built into all of our devices. And then we have this roadmap I showed you for the soft CPUs. Okay. So in summary, we told you about the Libero design suite, gave you a quick overview of that, and then we went through the embedded design flow for Mi-5 using SoftConsole. So I gave you a little bit of an overview of SoftConsole, did a demo, kind of showed you some of the features in there, and then showed you how you would go through and really take advantage of an existing project in order to run an application on your board. But you could do the very same thing by creating a project from scratch, and if you created a project from scratch, you would have to use the Firmware Catalog to create your drivers in your RISC-V HAL, and you would have to go through all the project settings and then create your debug configuration. So the example projects are a really good place to start, since you can just sort of copy those settings when you create your project from scratch. So we have, I think, everything in place that you need to let you to adopt RISC-V today. You can go off, use the ecosystem, get the tools. You can get evaluation versions of Libero SoC that you can start playing around with. SoftConsole's free. Firmware Catalog's free. We have the Github site where you can get lots of different examples, and we have tutorials.